Welcome to the class on HVDC transmission system. In this lecture, we are going to discuss about the faults in HVDC converters. First, we are going to see how these faults will be occurs in HVDC system. There are two ways in which the fault will be occurs in HVDC system. One is the malfunctioning of the equipment and control system. Second one is the failure of insulation due to the external source like lightning. So whatever the fault is occurs in HVDC system that we can able to identify, and we can rectify that fault by means of a control system and converter, so that the power interruption in HVDC system will be minimum. There are various faults will be occurs in HVDC system. Because of the fault, high amount of current is passing through the valves in a converter. The valve is a very sensitive device. If the current is more means the losses occurs in a valve will be more, which increases the junction temperature. The valve will be damaged. It is also sensitive to the over voltage. So such a type of faults we can able to identify and rectify and resume the HVDC system into the normal working condition. There are three different types of faults will be occurs in a HVDC system. One is the fault due to the malfunctioning of the valve and controller, commutation failure, and a short circuit in a converter station. The fault due to the malfunctioning of the valve and the controller is divided into the arc backs in a mercury arc rectifier, arc through, misfire, and quenching or current extension faults. Now we are going to see one by one. First, arc back in a mercury arc rectifier. This is the mercury arc rectifier. Arc back means this valve is allowing a current in a reverse direction. Some duration it failed to operate as a rectifier. Generally, this type of fault will be occurs in a mercury arc rectifier. It is a random fault. It is a non-self-clearing fault. More stress will be developed in a transformer winding if the arc back is occurs in a mercury arc rectifier. Nowadays, mercury arc rectifiers we are not using. We are using only the semiconductor device. So this type of faults will not be occurs in a semiconductor device. Commutation failure. To explain the commutation failure, here we have taken the 6-pulse converter. These are nothing but positive group of the device. These are nothing but a negative group of the device. The sequence of firing of the valves is the S1, S2, S3, S4, S5, S6. So every valve has a turn off device. Because limited turn off device, it requires a minimum extension angle. If the minimum extension angle is not maintained, then the commutation failure will be occurs in a valve. The extension angle is defined as a 180 degrees minus alpha minus mu. Alpha is nothing but a firing angle, whereas mu is nothing but a overlap angle. The overlap angle is highly depending upon the two parameters. One is the DC link current, other one is the computational voltage. If the DC link current is increases and the computation voltage decreases, means the overlap angle will be increases. So the extension angle will be decreases. If this extension angle falls below the minimum extension angle, then the computation failure will be occurs in a particular device in a circuit. Let us take the S1 and S2 is conducting. Now we are assuming that the computation failure is occurred at S1. The S3 is also on. The current through the S3 comes to the 0. The next device is the S4. Even though S3 is off, the S1 is continue to conduct because of the computation failure. After the S3, we are giving the firing pass to the S4. So whenever we are giving the firing voltage to the S4, then the S4 also will be conducting. Nothing but the commutation from the S2 to the S4 is completed. On the same leg, the two devices are conducting, that is S1 and the S4. Nothing but simply making short across the supply, AC supply. So the AC current is 0. The DC voltage also will be 0, but the DC current will be increases. The next awning device is the S5. Whenever we are giving a firing pulse to the S5, by the time the S5 is reverse biased because the voltage across the S5 is CA rather than the CB. The voltage CA is leads the CB, so the S5 is reverse biased, does not goes to the on state. Again, the S1 and S4 is continue to conduct. The next device awning device is the S6 in the sequence. So if you are giving a first to the S6, the S6 goes to the on. Nothing but one cyclic operation of the converter is completed. After the sequence is completed, the cause of commutation failure S1 is disappeared. So the bridge operation turns into the normal operation. The single commutation failure is a self-clearing. The waveform of the bridge voltage and waveform of the voltage across the walls are given here. This is the voltage across the second device. This is the voltage across the third device, fourth, fifth, sixth device. This is the voltage given by the bridge. The single commutation is failure is occurred. Effect of single commutation failure. The two effects will be occurs due to the single commutation failure. One is during the one cyclic operation, one third time of the cycle, the bridge voltage is 0. During that interval, the DC current is tends to increase. If the single commutation failure occurs, no current is passing through the walls in the same arm which are conducted. Now we are going to see how we are going to recover the single commutation failure means control of gamma angle at inverter station. Next, current control in the link. Third one is the magnitude of the AC voltage. So whenever we are identifying the single commutation failure, we have to increase the gamma angle of the inverter to the highest value. We can avoid the subsequent commutation failure in bridge. It is also depending upon the DC link current and AC voltage. We can ramp up the DC link current by controlling the inverter, but it will be limited by the smoothing reactor. So we can easily increase the DC link current by controlling the rectifier so that we can avoid the commutation failure. Mostly the commutation failure is self-clearing. If it is persistent commutation failure occurs in a bridge, then we are going to remove that bridge from the remaining series connected bridges in HVDC station. Arc through. This is the type of fault which generally occurs in a inverter station. If the valve is conducting, if it is not supposed to conduct, then that fault is nothing but a arc through. So here we are assuming that S1 and S2 is conducting. Now after the S2 we are giving a firing pass to the S3. So the current from the S1 is given to the S3. S1 will be off, where the S3 will be on. So whenever the S1 is off, the voltage across the S1 is negative. After some time, the voltage across the S1 becomes a positive by the time S3 is conducting. In that duration, if we are applying the firing pulse to the S1 due to any fault in a triggering circuit, then again the S1 goes to the on state. By the time what happened is the current through the S1 again given back to the S1. Nothing but S3 will be off. Now the S1 will be conducting. Next device we are going to give the triggering pulse is the S4. The S4 is on the same leg. S1 and S4 is conducting. Again simply making short across the supply. The AC current is 0. The DC voltage is 0. The DC current will be increases as like a commutation failure. Again this fault can be recovered after the S3 is fired. Single arc through is a self-clearing fault. The effect of arc through is similar to the commutation failure. Misfire. Misfire means we are applying the triggering voltage to valve to on it. If the given triggering pulse is not able to on the particular valve, is nothing but a misfire. The misfire is occurs because of the pulse which is not sufficient to the on the wall, whereas the arc through is occurs due to the unwanted triggering pulse. That is the difference between the misfire and arc pulse. The misfire can occur both in the rectifier as well as inverter station. The misfire occurs at inverter injecting AC voltage into the DC side, whereas the DC side is consisting of both inductance and capacitance, which forms a underdamped circuit, which giving a large oscillations to the DC current as well as the voltage in a DC link. The DC current may extinguish and results a high voltage across the wall. The wall may be the damaged. See here, initially S1, S2 is conducting. Now we are giving to firing pass to the S3 to on it, but S3 is not on. So S1, S2 is conducting. After the S3, we have to give the triggering voltage to the S4. Once the S4 is on the same leg, S1, S4 is conducting. Again, it's simply making short across the supply. AC current is 0, DC voltage is 0, but the DC current will be increases. Next, after S4, we have to give the triggering voltage to S5, but S5 is not going to the on state because it is a reverse bias. After the S5, we have to apply the triggering voltage to S6. Now the S6 is on, S4 will be commutated. Now the S1 and S6 is conducted. Nothing but a misfire will be disappear after the one cyclic operation. It is also self-clearing fault. It is also similar to the arc through and the commutation failure. Current extension. Current extension is nothing but when the valve is on, the current is passing through the valve in a bit. The current may be come to the zero. If the DC link current is zero, the current passing through the valve is zero. If any transients occurs in a valve in a circuit, the current may come to the zero. So the valve may be turns off. This is nothing but a current extension. The current extension results over a voltage across a valve due to the chopping of current in an oscillatory circuit formed by the smoothing reactor and DC link capacitor. Next, short circuit in a bridge. Generally, the short circuit in a bridge will not be occurs because all bridges were keeping in a air condition. But in some cases, there may be a short circuit across the brushings of the bridge, which causes the high peak current through the wall, which may be damaged. Short circuit generally occurs in a bridge rectifier circuit. The maximum short circuit current is passing through the wall when the firing angle is 0. The waveform of the current passing through the wall during the short circuit is shown here. This is the DC link current, reaches the maximum value, again it comes to the 0 at this point. This peak current divided by the IS, nothing but source current, equal to 3 by 2 plus ID naught by 2 IS. This is the relation between the peak current and AC side current and ID naught, nothing but this current before the short circuit. IS equal to root 2 ELL by A 2 XS, where XS is nothing but a reactance of a transformer. So thank you very much. In this lecture we have discussed about what are the different types of faults which may occur in a HVDC system.